So you see the title of my talk here. I will be talking today about robust fitting and smoothing parameter selection for the class of generalized additive models for location, scale, and shape. So it's a mouthful. I will be referring to that class as GAMLSS. That's the official acronym here. And this is joint work with Eva Cantoni from the University of Geneva, Giampiero Mara, which I suppose most of you know well, and Rosalba Radice from the City University of London. By the way, feel free to interrupt me. I think it's nice if we can have more of a conversation rather than a unilateral speech here. So yeah, I guess I don't think I can see if you raise your hand, so you should probably just speak with your mic, and that would be enough for me to stop and listen to the question. So the outline seems a bit daunting like this, but I really divided everything into small chunks for today. Mainly, I will be introducing to the motivations of this work, trying to convince you that the problem we're addressing is actually worthwhile. Then I'll get into the details of the proposed method. I'll touch upon a few specific aspects of our work, which I think are quite novel, if not at least useful in their own right. And then I'll present you some results from simulations and an application to brain imaging, which was part of the motivation of this work. So let me maybe start by stating the overarching goal here. The goal of this kind of work is to estimate smooth functions, also known as non-parametric effects or just nonlinear effects. So we are in the context where we have a response variable, which is the variable of interest, something we want to model. And we have other variables, which we will assume fixed, which I will just denote by covariates in a general sense. So those non-parametric effects would be the effects of these covariates on the response variable. Now, there is a key word here. We want to do this estimation of smooth function in a reliable way. And reliable is, of course, the important one that which refers to robustness, which is the main topic of this talk. And I'll define it a bit more in detail in a minute. If you think of the traditional way of fitting such models, you would think of some objective function, say a likelihood function, that you would penalize or regularize to achieve some kind of smoothness. The issue with this traditional or these traditional estimating methods is the impact of deviations from model assumptions. Of course, maximum likelihood has a lot of optimal properties, but they rely on the validity of the assumptions we're making to be true. If they're not, well, we don't really know what's going to happen. In general, we can expect that estimates will be biased, that inference may be completely wrong. So this is something we're generally trying to address here. For the class of GAMLSS, there is no robust estimating method as far as we know. But there are quite a few that have been proposed in the last 10 years or so for the narrower class of GAMs, generalized additive models. I'm citing here 3 papers, which are the 3 main methods I will compare our method to in a simulation study later on. Now, there are 2 things that haven't been addressed really, I think, in the non-parametrics literature that is related to robustness. One is how we can select smoothing parameters in a robust way, but also in an automated way. Here, the issue we're facing is that, yes, there exists some robust versions of archaic information criterion, for instance, or robust cross-validation, but they are computationally very prohibitive. It requires a lot of computations, typically grid searchers. And if you have many smoothing parameters you want to estimate, this simply becomes not feasible. So there is definitely some room for improvement here, I would say. And the second issue I will touch upon today is the issue of tuning robust estimators. I can say this in pretty general terms that the vast majority of robust estimating methods do require some calibration. There is a trade-off that has to be achieved when computing such an estimator. It's a trade-off between something we typically lose if the data were to come exactly from the assumed model and something we gain, which is a robustness property. So this idea of tuning has been traditionally based on efficiency. So basically comparing covariances between a robust estimator and some non-robust benchmark, maximum likelihood estimator typically. But in the non-parametric setting, these covariances are typically not comparable. So we are left with this challenge of finding a new way to tune robust estimators, which is meaningful and which is also general enough so that we can compare potentially many different robust estimating methods in the same setting. Now, I'm using the word robust, and I acknowledge that there are various meanings for that word. So I think it's worth taking a bit of time here just to make sure we're all on the same page. I am using the word robust here in the statistical sense that you would see in literatures. If you think of the textbooks of Frank Hampel and collaborators, Ricardo Marona, Peter Huber, and there are, of course, quite a few in this literature vein. I can briefly summarize the setting as follows. You have a core model, which in this case is represented by f theta. So let's just assume for simplicity that this is a parametric model. So theta would be your parameter of interest. You want to make inference about this. F theta is the model, but you don't really assume that the data at hand comes from f theta. Rather, you would assume it comes from a mixture, which we denote by f epsilon here. Epsilon represents some contamination proportion. What you're essentially saying here is that the majority of the data should come from the assumed model, but there is nonetheless a small part of that data that may come from something else, another distribution, which typically is arbitrary, G in this case. Now, of course, if you knew what these data were, if you know what the so-called contaminating data points were, you would typically try to model them explicitly. I mean, mixture models are here for a reason. That's not what we're going to do today. Here today, we would assume that f theta is really the central model. It is assumed good enough for the majority of the data. What we really want to do is compute quantities under that model that remain meaningful, even though there may be a small proportion of the data that comes from some arbitrary distribution G. Now, no prior knowledge is required about G. And also, we don't require to know which are the data points that may come from G. In fact, the robust method can be used as a diagnostic tool to know which data points may be different from the others in terms of their data generating process. A last point I want to make here is something that may seem obvious for many of you, but it can become subtle once you get into more complex models. And it is the distinction between robust estimation and trying to increase the flexibility of a model. To be clear, in the robust estimation context, you typically have a model, f theta, which is considered good enough, and you stick to it. The only thing that changes is the way you compute things, the way you estimate parameters or compute confidence intervals and whatnot. These would be computed in a different way. If you think your model lacks flexibility, then what you should do is change your model altogether, and then maybe compute things as usual, for instance. This is quite different. In essence, it really boils down to how large that epsilon may be. If it's only a few data points out of 100, I guess you could get away with saying that f theta is good enough. If it's, I don't know, 30%, 40% of your data, you should change your model altogether, right? It's really a lack of fit that you're facing here rather than some sensitivity issue due to just a few data points. So today we will not be discussing really the flexibility issue. We will really be discussing how we can compute things in a robust way for a given model, being a GAMLSS today. Now a bit about this application that motivated us to dig into this. These are data from a early 2000 study. It was about having patients subject to some external stimuli and measuring the activity of their brain, essentially. But I think the investigators were really after trying to find differences between distinct regions of the brain, and especially in the timing and in how fast they were reacting to the stimuli, and across a bunch of them, of course. So we will not be looking today at the entire time series of brain images. This would be, of course, very interesting. Here we're just looking at a single brain slice, so just one image, a 2D image, where we would typically model both the mean activation level, the mean physiological response, if you will, but also the spread. The reason we're looking at these data is that Simon Wood used these data as an illustration that appeared in, I think it was the second edition of his book in 2017. What he did is he used these data, the single braid slice, but he removed 2 data points. And I'll be honest with you, I found his justification in the book not really convincing. He's basically claiming that these 2 data points, these 2 voxels, were below a certain threshold, and that's pretty much it. Honestly, I don't remember that there was any more justification from a scientific point of view. Maybe there is, by the way. I'm not claiming this is just plain wrong. It's just I wasn't convinced the first time I read this. As a statistician who works in robustness, my first reflex when I read this is, oh, well, we should be modeling this and estimating things in a robust way. If it's just a few data points, which may be different from some reason and we cannot explain it, well, we might as well compute things in a robust way. So this was kind of the motivating application that I'll present near the end of the talk. All right, I think it's worth defining this class of GAMLSS a little bit better. So we have a response vector, y1 up to yn. Each of these random variables are univariate for the sake of simplicity, really. There is human independent. I could give a few words near the end if you're interested to discuss how we could relax this. But really the core of the GAMLSS is the distributional assumption we're making about each of these yi's. So we assume they come from a certain distribution, D, and in the canonical form, this distribution D depends on 3 parameters. Obviously, nothing is preventing you from going to more than 3 or less than 3. 3 is just the standard poster child of the GAMLSS, if you will. The first parameter identifies some kind of location. The second parameter is a scale parameter, typically, and the third one would be a so-called shape parameter. Now, the real flexibility of the GAMLSS is that each of these parameters is then modeled explicitly as a function of covariates. All the x's I have here are explanatory variables, and the s's in which they enter are smooth functions which we want to approximate. So these are not linear functions typically, but they're unknown nonetheless. What can we do? We typically approximate those s's by linear combinations of some basis functions. Now, I will assume that the number of bases we use for each effect is large enough. Okay, we will not get into too much of the details of approximation error for the function itself. And also, I will not discuss too much what kind of bases you should use. Obviously, the data analyst should use something that is appropriate for the task at hand. But just to be clear, any kind of basis could be used here, whether it's Fourier polynomials or splines, which we will be using in the talk. Now, the coefficients, the betas that appear in each of those linear combinations have an associated quadratic penalty, okay? The reason here is that, yes, you want to be flexible in the way you can approximate some complicated function, but you don't want your estimated function to be too wiggly, okay? We want to penalize the wiggliness, and we do so by using such a ridge type penalty, just a quadratic form in the betas. And yes, this quadratic form is tuned by a lambda parameter, which I will call the smoothing parameter. All the betas, so basically all the parameters in my model are then stacked into one big vector, which I'll call delta. And from the assumptions of the model, you can construct a log likelihood function, L of delta. Now, all the smoothing parameters, all the lambdas, I am also going to stack them into one big vector, which is just called lambda with no subscript. And I can then write the model in a fairly compact way as my log likelihood for the model. Here it is. And the quadratic penalty, the ridge penalty with this S matrix here, S of lambda, which is block diagonal, and each of the blocks being themselves block diagonal typically, and typically linear functions of the lambdas. They appear directly as linear functions in each of these elements. So these two ingredients taken together form the penalized likelihood function, which you would typically maximize in the traditional estimating framework. Now, what can you do to estimate things in a robust way? The trick here comes from a paper that's not so much well known. It's a technical report actually from the early 2000s by Iguchi and Kano. And the idea is actually fairly intuitive. The idea is to apply some function rho on each of the log likelihood contributions. The goal of this rho function is to reduce low log likelihood values for a given value of delta, while at the same time leaving the high log likelihood values essentially unchanged. So we're using the actual log likelihood value as a criterion for, I guess you could call it, agreement between what you observe, the actual data, and what you expect given a model, right? In the same way you could use a residual in a linear regression setting, here we're using the log likelihood value itself as this metric for judging agreement or disagreement. The additional term here, B of rho, is a correction term that's there to guarantee Fisher consistency. Essentially, we want to make sure that if the data do come entirely from the assumed model, basically epsilon is 0, we want the estimator to still be unbiased, right, asymptotically. This rho, I will not be discussing it too much. It's defined as an expectation. It's a bit messy because you need to approximate a unidimensional integral, but it is definitely feasible with the tools we have nowadays. I mean, within the R package we are using, it is done seamlessly in the background. An example of a rho function that works well for our task is the so-called log-logistic function that Iguchi and Kano introduced. And I'm representing it here. So on the left-hand side, you have the log-logistic rho function. And on the right-hand side, I have the first derivative. So again, think of it this way. If my log likelihood is high, I should basically not touch this, right? The observation should contribute fully to the overall, the data log likelihood, and thus to the estimation process. But if my log likelihood is low on the left-hand side, you see that my rho function here tends to level off, meaning the corresponding observation will contribute less and less, relatively speaking. You have a similar interpretation if you think of estimating equations, and that's where the right-hand panel here is useful to look at. So the first derivative of rho can be interpreted as a weight. The conditions we enforce on rho is that the first derivative should be bounded between 0 and 1. And here you can explicitly see the sigmoid we get with the log-logistic function. So again, for large log likelihood values, my weights will be very close to 1. And for low log likelihood values, the observation will get downweighted more and more. From this robustified log likelihood, we can then formulate a penalized robustified log likelihood, which is basically replacing the original log likelihood I had with the robustified version with the tilde on top, but keeping the penalty exactly as it was. The reason is the penalty does not depend on the data. There is no reason to change it. And from there, we can define our robust estimator delta hat. We can equivalently define it under some conditions at the estimating equation level. So it would be the value of delta that solves this equation down there. And again, you find all the usual terms. You have the smoothing matrix here. You have the derivative of the correction term, which is also an expectation we need to approximate. But then you have the maximum likelihood score here, the derivative of the log likelihood, which multiplies this weight I just mentioned earlier. Rho prime is the first derivative of the rho function. And this guarantees the robustness property of the estimator here. There are a few theoretical properties that I will just mention. I don't think it's really worth going too much into the details, but it's good to know that they are there. So the robust estimator can be shown to converge to the true parameter under conditions. It is also asymptotically normal with the usual sandwich formula, M inverse Q, M inverse here. There should be a minus sign here. And maybe more importantly, the influence function is an interesting result to look at. So for those of you who are not so familiar with the robustness literature, the influence function is one of many tools that people use to basically quantify some robustness property for estimators. In this case, the influence function is quite useful because if you can show that it is a bounded function, it implies that the maximum bias that the estimator can endure under the worst case scenario of a point mass contamination is bounded itself. So here, this is exactly the result we get. Thanks to this rho prime being bounded between 0 and 1, we have a bounded influence function, and thus we know that the maximum bias that the estimator can have is bounded itself. It's not guaranteed to be 0, though, but at least we know that the estimator cannot be drawn to arbitrary values, just like the maximum likelihood estimator could. Now I want to discuss a little bit these two challenges I mentioned earlier, which haven't really been addressed so far in the literature. One is the smoothing parameter selection. So from the robustification scheme I just explained, arises in a natural way, really, some Akaike information in criterion, an AIC, which is robust itself. It directly comes out if you use the GIC kind of framework from Konishi and Kitagawa. And it has the usual functional form, really. It's minus twice the robustified log likelihood here, plus 2 times a term which quantifies the effective degrees of freedom. So it's this trace of the matrices M, S, and Q here. So what I think is quite nice is that this criterion directly comes from the fact that we robustify at the objective function level. Most of the other schemes that you would find for generalized linear models or generalized additive models is to robustify at the score level, which means that you don't necessarily have a robust AIC that arises naturally from the objective function you've constructed. Nonetheless, as I mentioned earlier, working with an AIC, whether it's robust or not, has some issues. Again, if your lambda parameter, or sorry, your lambda vector is very large, doing grid searches for each of these components become just unfeasible. So this has led us to look into alternatives. And yes, there has been one fairly recently in this paper by Simon Wood and Matteo Faziolo, which is actually quite promising for us. So they basically revisited an idea that the authors Fellner and Schall have developed, I think it was in the late 80s, if I'm not wrong. And what we've done following their paper is to extend it to the robust estimation scheme. So we call this the extended Fellner-Schall method. And I think it's worth going through the steps a little bit together because it gives us some interesting insights. So the starting point is a robustified log likelihood, so the L tilde I introduced earlier. We can view the exponential of that as some kind of density up to normalization constant. So it's not, it does not integrate to 1, but it does integrate to a constant, and it's always non-negative. So it can be seen as an improper density if you want. Next, you consider the quadratic penalty, the ridge penalty here, as an improper multivariate Gaussian prior on delta. So we are taking this Bayesian, or maybe I should say empirical Bayes view, where now both the response y and delta are both considered random, and lambda, my smoothing parameter, is seen as another model parameter. We can construct a joint log density, this is what I have down there, for both y and delta taken jointly, which is nothing more than the previous robustified log likelihood I had. So this is exactly what I had on the previous slide. But now I add this extra term, which involves only S of lambda. So S of lambda in this empirical Bayes setting is really the precision matrix of my delta vector, considering a multivariate Gaussian distribution. Note that because this extra term does not depend on delta at all, I could also define my robust estimator as the maximizer of this joint log density. There is nothing wrong, it's the exact same value. Next, we have a joint density for y and delta, but the delta are unknown. So what do? Well, we integrate them out. This is the marginal density I'm defining here. But the issue here is that delta is typically of fairly high dimensions. If you have multiple covariates, multiple canonical parameters you want to model, you may end up with a pretty high dimensional integral here, which obviously in general cannot be solved explicitly. You need to resort to some approximation. Here we are following the development in the paper by Simon Wood and Matteo Faziolo. We're using Laplace's method. It's probably one of the simplest approximations you can think of. It is essentially a second order Taylor expansion of the log integrand here. And we're taking the expansion about a global maximizer. The maximizer for delta here being in fact the robust estimator I just introduced. So because the expansion is taking about a maximum, the first order term vanishes, it's zero gradient, and we're left with the second order term, which is essentially the kernel of a multivariate Gaussian. And this allows us to write the Laplace approximated marginal robustified log likelihood like this. Essentially, we've plugged in delta hats, which can be computed for a given lambda. We still have the same term here. And now we have an extra term, this calligraphic H, which is the negative Hessian in this case, but only involves S of lambda, which we know, and the numerical Hessian of the robustified log likelihood, which is typically something you can compute by hand. So we're not done yet. We have this Laplace approximated marginal. Let's look at first order conditions. Again, the goal here is to be able to update lambda as if it were a parameter. So take the gradient, not the gradient, just the derivative with respect to one entry, lambda j. This is the expression you get. It is quite messy, but it is especially messy because lambda appears pretty much everywhere. It appears explicitly through S of lambda. It is a direct function. So this S matrix, the smoothing matrix, is a direct function of lambda. But lambda also appears implicitly through delta hat. Remember, if I just go back one slide, this is the point around which I'm taking my Taylor expansion, but it is computed for a given value of lambda. So there is an implicit dependence on lambda here that should be taken into account. This is not easy to tackle. We need to approximate things a bit further here. And what we're doing here is that we're neglecting the dependence of delta hat on lambda. And the trick here is to cast this, this first order derivative in an iterative scheme. What we're going to have now are two versions of lambda. One version which comes from the previous iteration, which I'll denote by lambda tilde. So it's not a derivative, it's just a fixed value of lambda here. So this value is inactive. And then there is the current value of lambda, the one I'm using to do the update, or towards which I'm getting the update. And this will just be a plain lambda. So this is my new Laplace approximated function here with two versions of lambda, the active one and the inactive one. Any quantity that depends on the inactive one is considered a constant with respect to the derivative with respect to lambda j. And this allows us to simplify things a lot. We get this new expression down there, in which now you see some delta hats, which are just fixed constants here. They're just functions of the previous value of lambda. And then you have the current value of lambda, which we will include for the update on lambda. Now, we're not done yet, because even this gradient here is not so easy to tackle. For instance, trying to embed this into some Newton-Raphson scheme is not easy. In general, you will not be able to make it work, or at least make it numerically stable enough. So we've followed the reasoning that Simon Wood and Matteo Faziolo did in their paper. And it's really a reasoning based on necessary conditions. Basically, there are four conditions that we want the update to satisfy. One is that if the gradient or the approximate gradient is 0 or arbitrarily close to 0, then the update should not change anything. Fair enough. Next, second condition, we want whenever the gradient is positive, we want the update to increase the value of lambda. Remember, we're actually maximizing a function here. Conversely, third condition, if the gradient is negative, we want to decrease the value of lambda. And last, we want the update to guarantee lambda will always remain positive. These are the only four conditions we want. And based on these, we can construct a heuristic update, which is actually very close to the expression that they had in their paper, except that here it relies on robustified quantities. So it's basically taking the previous iterate of lambda and multiplying it by some ratio to get the new value of the iterate. This ratio is guaranteed to be positive. It is between 0 and 1 whenever the gradient is negative, and it is greater than 1 whenever the gradient is positive. So it is really satisfying all the necessary conditions, and it is actually working quite well in practice. This is the EFS method we have implemented in the R package. And I should say something which is quite nice is all the quantities you see here in this ratio, I think pretty much all of them are quantities that are anyway computed whenever we carry on the optimization for delta for a given value of lambda. So they are already there, to be fair. So it doesn't add a lot of computational overhead to include this update of lambda if you think of an alternating scheme, updating delta given lambda, updating lambda given delta. And this is what this EFS method do. It allows basically for an automated selection of the smoothing parameter by taking this empirical Bayes viewpoint. And as you'll see in a minute in the simulations, it actually performs fairly well and at a fraction of the computational cost of a grid search, really. The second issue I wanted to discuss a bit more in detail today is this issue of tuning. As I already summarized a bit at the beginning, a robust estimator needs to be tuned or calibrated for a certain trade-off. If you think of a parametric model where maximum likelihood would be your benchmark, the way it was done pretty much all the time so far was to look at asymptotic variances or covariances, take the trace and take a ratio of those traces. And this would be your efficiency criterion. To be clear, this criterion is to be computed whenever the data do come from the assumed model, okay? The idea is that you would lose some efficiency at the model, at the assumed model, but in order to gain robustness whenever the data does not entirely come from the assumed model. Okay, so it's kind of an insurance premium, really. You have to pay something up front to guarantee you will protect yourself against some risk in case the data do not come from the postulated model. Now, the issue we're facing here is that these asymptotic covariances are only meaningful in parametric models, really. If you have non-parametric effects, typically your lambdas will be different between the two estimators you're comparing. So the two covariances will actually not be directly comparable. What can we do? This is where we introduced I think, fairly simple and effective new criterion for tuning estimators. We call it the median downweighting proportion, MDP for short. And the heuristic idea is really to quantify how much downweighting is happening if the data exactly come from the assumed model. And to do this, we actually simulate. We don't use asymptotic formulas. And I can actually show you the recipe here. It's actually fairly easy to describe. First, you need to pick a value of your tuning constant C. So pick any value. You have to do. We'll have to do a bit of trial and error here. With this value of C, you can compute your robust estimator on the original data, and you can also find the optimal smoothing parameter here for a given value of C again. Next, we're going to simulate data. We're going to simulate data using delta hat as the generating parameter. And we're, of course, going to simulate at the assumed model. We're going to do this capital B times. And on each of the Monte Carlo samples, we actually don't estimate anything. We just evaluate the weight here given by this rho prime function. This is very cheap to compute, right? There is no optimization involved. It's just a matter of evaluating this. Usually it's a closed form formula. And then we compute the average weight for that particular sample. So you can think of it this way. If all the weights were equal to 1, then this WB here will be equal to 1 itself, right? Because you would just be summing n ones and then dividing by n. So this WB essentially gives you a metric of how much downweighting happened for that particular Monte Carlo sample. But then you want to average things out a little bit over multiple samples. Here we recommend to take a median across the capital B Monte Carlo samples, and hence the name median downweighting proportion. You can, of course, compute a mean also, but I would say if the model is fairly complex, you could have a few data sets that were generated at the model that behave a bit more erratically than others. So it's probable that taking a median is a bit safer, just from a numerical stability point of view. So to be clear, you started from a value of C, and the output you get here is this median downweighting proportion. Then the recipe is to repeat these 3 steps and move the value of C until you reach an MDP, which is some kind of target value. For instance, you would like your MDP to be 0.95. Okay, so you will do some trial and error to find the C that gives you an MDP of 0.95, for instance. So this is really based on heuristics. in order to justify a bit better this choice, I can show you what happens when you apply this in a context where the traditional criterion of efficiency can be computed explicitly. And yes, the setting is linear regression. So here I'm considering two estimators, the maximum likelihood estimator under a Gaussian assumption, okay, traditional x transpose x, inverse x transpose y. And as a robust estimator here, I'm using probably the simplest robust estimator there is, which is the so-called Huber estimator, where you basically bound your residual by the Huber psi function and solve these estimating equations for beta. So under this simpler setting, the efficiency of the robust estimator with respect to the maximum likelihood estimator can be computed explicitly. It's this ratio of traces here, and you have the formula down there. It only involves the tuning constant C and the standard normal CDF and PDF, really. That's all there is. So you can evaluate this right away. The MDP, well, it's simulation based. So technically there is no closed formula in finite sample, but we can look at what happens asymptotically here. So if you take the mean downweighting proportion, which is just easier, so as both the number of bootstrap samples and the sample size go to infinity, yes, this is just an average. It converges in probability to some expectation. Here, the expectation is taken for the some generic weight, which is based on a residual that just has a normal 0-1 distribution. We can compute this expectation explicitly. It's this formula down there. Again, it involves the standard normal CDF, the tuning constant C, and well, there is also this operating complete gamma function. No big deal. We can evaluate everything numerically right away. So I can show you now the two curves corresponding to the traditional efficiency and the asymptotic MDP here. So the black solid line is the standard efficiency, and the red dashed line is the MDP criterion. The important thing to notice is that they're both monotonically increasing, meaning that between the two criterion, there is a one-to-one relationship. In other words, if you are targeting for a certain asymptotic efficiency, there is one and only one value of C, but there is only one and only one value of the MDP. And conversely, if you're targeting a certain MDP, there is just one value of C that will correspond to it, and there is one and only one efficiency that corresponds to it. So this one-to-one mapping between the two criterion is really the main justification. Of course, we've developed this for a non-parametric setting where the efficiency is not really meaningful, but we just realized that the MDP could be used also in parametric settings and would probably lead to the same results. I can now move on to simulations to illustrate a bit all the stuff I've been discussing so far. So here I'm presenting simulations in the GAM special case. The reason is that I want to compare our method to others that have been already proposed, the 3 papers I mentioned earlier. So here I'm taking the design from the most recent of those 3 papers, from this paper of Raymond Wong in 2014. So here the response variable follows a Poisson distribution. They're all independent. And the mean UI has a log link, unsurprisingly. And there is only one covariate really involved here, xi. And the smooth function we're trying to approximate is basically a sine wave. Okay, it's a single period of it that we're trying to capture in a non-parametric way. Now I'm going to simulate data at the model, at the Poisson distribution, but I'm also going to contaminate the distribution, right? And here I'm also following what Wong and his collaborators did. I'm selecting at random 5% or 10% of the generated counts, and then I'm moving them to the nearest integer subject to this funny looking scheme here. So I'm generating a uniform between 2 and 5, but then I can flip the sign with a second uniform. So either increasing the original count to a larger count or decreasing it towards 0, but never going into negative values. So again, the contamination itself doesn't really matter as long as it is different from the original data generating process. We should see some effect. I'm going to consider 7 different estimators. It's quite an extensive study we did here. So there is the method introduced by Matias Salibin Barrera and his collaborator, which we'll call AS. This is based on, it's really a robustification of the backfitting algorithm for GAMS. And it is based on a brute force cross-validation scheme to select the smoothing parameter. It's actually quite slow. It takes a lot of time. But in this case, we were able to make it work. So it was worth including it in the study. CGP is another method by Christoph Krux and his collaborators. Here, this is based on a quasi-likelihood estimating, robustified estimating equation. And they have a sort of an ad hoc generalized cross-validation criterion here to select the smoothing parameter. WYL is the method from Wong and his collaborators. This is also based on a quasi-likelihood framework. It actually goes back to the way robust estimation was designed for generalized linear models, where you can rephrase everything into an iterated, reweighted least squares algorithm. Here we are using the robust version of BIC for the selection of smoothing parameter. The reason is that it was the best performing in their study, so we just took their best flavor, let's say. Next, we have 3 variants of our method. The reason is that we're varying how we select the smoothing parameter. So we have this robust AIC, we have a robust BIC as well, and the EFS method I described earlier. And last but not least, we have the classical, the maximum likelihood or penalized maximum likelihood estimation method as the usual benchmark, of course. Now, the important thing here is that in this study, thanks to this new criterion MDP, we are now able to tune all the various estimating methods so that they are comparable, something that hasn't been done in the previous studies. So they are all tuned to have the same MDP of 0.95, and that results in various values of their tuning constants. They're all a bit different because, well, the schemes are different, but they are comparable in terms of how robust they are. I'm showing you box plots of empirical mean squared errors. So each of the box is taken over the 200 replications we did for each sample. And there are 3 subpanels. The one to the left is when I simulate data at the assumed model, the Poisson distribution. The panel in the middle is for 5% contamination. And the panel on the right is when I select 10% of my sample and contaminate them. So first at the model, unsurprisingly, the classical method performs best. That's the optimal property of maximum likelihood. But of course, when you start contaminating this, the MSE goes through the roof. I mean, on the 3rd panel, it's literally out of the chart. So this is, again, not surprising at all. What is more interesting is to see how the various robust methods perform. AS tends to vary a lot. It might be due to the cross-validation scheme, but it is still fairly stable. I would say that the median mean squared error is slightly smaller for CGP in our method. They also vary less. They're actually, I would say, all of them kind of similar. We're really looking at tiny details here. I will not claim that our method performs better, but what is really reassuring, I would say, is that it's not worse than the best performing method there is out there. Again, remember, this is a special case of GAMLSS. This is just a generalized additive model. And for us, it was actually very important to make sure that what we're proposing for the broader GAMLSS was not worse than what already existed for the special case of the GAM. And this seems to support this idea. All right, so I'm back to this brain imaging application now. So just to remind you what it was about, we have a single brain slice of really the response variable really being the physiological activation of each voxel. The only covariates we have are the X and Y axis. So basically the position, the location of each voxel. We don't have any external covariates to use here. And the entire brain slice has a bit over 1,500 data points. Now, it is quite a challenging modeling task here. The fMRI tends to be very noisy. It tends to pick up a lot of background noise. So we definitely need to smooth things fairly well. And then there is this other challenge, which I alluded to already, which is that certain voxels may behave completely differently. I mean, there is no guarantee that all the voxels react to the external, the lab control stimulus in a coherent way. I don't think it's reasonable to assume this. So again, as I mentioned, Simon Wood did exclude 2 data points based on the criterion that they were smaller than 5 times 10 to the minus 3. Okay, that was his rule of thumb. We keep those data points, and you'll see in a minute that the robust method can actually detect them. The model we're using here is a gamma distribution, where we model both the mean surface and the spread. So this second parameter we're also modeling, the scale parameter, is a multiplicative coefficient for the variance. So under this parameterization of the gamma distribution, the expectation is mu I, and the variance is sigma squared times mu I squared. Okay, it's a quadratic function in the variance. All right, here are the results. So I should explain a bit how to read this this figure. The top row represents the surfaces for the mean parameter, so for the first moment we're modeling. The bottom row are for the second parameter, for this spread, so modeling the variability really. The column on the left is for the classical fit, so the penalized maximum likelihood method, and the column on the right is for our robust method, tuned for an MDP of 0.95 again. So I think if you just look at it from a distance, you right away notice that the robust fits tend to be smoother, okay? Especially the bottom right panel, the variance may actually be considered constant across the plane here. But if you look at the top right, the interesting thing is that yes, it is flatter overall, but the points where, or the areas where we predict a higher activation basically coincide with what the maximum likelihood method does. So that's reassuring, but it definitely has a smaller magnitude. Notably, this top right corner here, where the maximum likelihood method predicts a fairly high a peak in activation, whereas the robust method would say that the activation there is not so much different than what you have in other places. Also, an important difference between the two methods is down there in the bottom left. You see this peak in the variance in the occipital lobe. Oh, maybe I should mention that the way to view this this map is that the person the brain we're looking at, the person would be looking on the right. Okay, so the frontal lobe would be at the right of each picture, while the occipital lobe would be on the left. So this peak here in variability that the maximum likelihood method predicts does not show up in the robust method. Okay, that's quite interesting too. We kind of predict that the variance should be flat elsewhere, whereas the maximum likelihood say uncertainty would be very large in this area. To understand this better, the robustness weights are our friend. So what I'm showing you here is a single slice, but each of the voxel is colored according to this robustness weight. So it's a value between 0 and 1. The yellow colored voxels are weights essentially equal to 1, meaning no downweighting. Whereas the closer you get to this dark purple shade, the more downweighting occurs. So yes, in the top right corner, when you saw this big difference here between the mean level of the two methods, this is where the robust method downweighted a lot. So what the methods found here is that these data points do not behave like the other data points if the task here at hand is to smooth things out. But also quite interestingly, this area here where I mentioned a large variance, we have something here. I guess I could zoom in maybe if you don't see it well. If you can see those two green crosses, those are the two data points that Simon Wood excluded from his study. So yes, the robust method here downweights these data points quite heavily, and they're really isolated from the others. So that's reassuring in the sense that we kind of get to the same conclusions as previous analyses. But the important thing to remember here is that the robust method objectively identified those. There was no arbitrary threshold or rule of thumb to decide whether these data points were valid or not. They are part of the data. They were used as part of the fit, but the method deemed them to be too different to be used fully in the estimating process. I think it is time for me to conclude. Oh yeah, I think we're right on time. So this talk was about a new robust estimation method for the entire class of GAMLSS. The main message here being that if you can fit your model by maximum likelihood, you can use our robust method too. Sure, there are a few components you need to compute, a few extra computational things to do, but from a conceptual point of view, there is nothing really hindering anything. The robust estimator is well defined for the entire class, really. The method is already implemented in this GJRM package, which is available on CRAN. I encourage you to check it out. This robust AIC as a natural byproduct was definitely a neat result for us, but I think the extended Fellner-Schall method as a more automated way to select smoothing parameters is really neat, for especially from a user point of view. The fact that people may not need to worry too much about it, it's being estimated as part of the fit. I think it's really useful to have this in the toolbox. Also, this median downweighting proportion criterion, I feel this would be very useful also in other contexts, especially given that it is simple, does not rely on asymptotics, and it is really inexpensive to compute. There is some future work for us, namely in studying more rigorously, I would say, the two things I introduced today here. So this MDP criterion definitely would warrant a bit more of a theoretical study. And also the EFS method. You probably noticed when I gave you the recipe there that it relies on several layers of approximations. There is this Laplace approximation for the integral, some dependence with neglect, and so on. It's not quite clear how the multiple approximation errors may compound. So I think it's quite important there to study this a bit more rigorously to also understand where the limits of such a method may be. And that is all for me. Thank you for your attention.